The Antikythera Mechanism. The year is 1901. Greek sponge divers descend into azure waters off the coast of Antikythera, a tiny island between Crete and mainland Greece. They surface with stories of bronze limbs reaching from the sea floor. Statues, they think. What they found is a Roman shipwreck from 87 BCE. What they don't know is that inside one corroded lump of bronze and wood lies a machine that will make archaeologists question everything they thought they knew about ancient technology. In 1902, archaeologist Valerios Stais examined the recovered artifacts stored in an Athens museum. Most were statues, pottery, coins. Then he noticed something odd embedded in a calcified rock, a gear wheel. For decades, it sat ignored until 1951, when physicist Derek de Solla Price began serious study. X-ray analysis in 1971 revealed the truth. This wasn't decoration, it was a computer. The Antikythera Mechanism contains at least 30 meshing bronze gears. Originally, it may have had 72 or more. The front dial shows the Greek zodiac and Egyptian calendar, with 365 days. The rear dials predict lunar and solar eclipses using the 223-month Saros cycle. It accounts for the moon's elliptical orbit using epicyclic gearing, a concept not rediscovered until Copernicus walked the Earth 1,400 years later. A 2006 study by Freeth and colleagues published in Nature revealed inscriptions describing athletic games, suggesting it also tracked Olympiad cycles. Michael Wright's 2002 reconstruction demonstrated it could track all 5 planets known to ancient Greeks, required precision machining to tolerances of fractions of a millimeter. No comparable technology appears in the historical record for 1,400 years, not until medieval Islamic astronomical clocks. Radiocarbon and stylistic dating place its construction between 150 and 100 BCE, possibly as early as 205 BCE. The device predicted planetary positions decades in advance. A 2021 study by University College London decoded its full gear system, confirming capabilities that rival pocket watches made in the 17th century. Mainstream historians argue it represents the peak of Greek mathematical astronomy and mechanical engineering. The Greeks had sophisticated knowledge of epicycles and gearing, evidenced by writings of Archimedes and Cicero's references to similar devices. It's extraordinary, but not impossible for Hellenistic craftsmen with access to mathematical treatises. The mechanism proves ancient people were smarter and more capable than we give them credit for. But no other artifact even approaches its complexity. Not one intermediate step exists in the archaeological record. Not one practice piece, not one simpler prototype, not one failed attempt gathering dust in a museum basement. The leap from known Greek technology to this is like jumping from an abacus to a laptop. Where are the workshops, the failed experiments, the gradual improvements you'd expect from any developing technology? Some researchers ask, was this the only one ever made, or the last survivor of a lost technological tradition? The sophistication suggests a long development history, decades or centuries of refinement. Yet archaeology shows no trace of it. The mechanism works too well to be a first attempt. It had to be the product of an established engineering lineage. Yet it stands utterly alone, separated from anything before or after by a chasm of silence. Who designed it, and where was the knowledge transmitted? Why does no literary source describe its construction methods? How many others existed that were melted down for scrap bronze or lost beneath the Mediterranean? We may never know. What we do know is that someone in the ancient world built a machine to map the cosmos. And when that world collapsed, the knowledge went with it. From a machine that mapped the stars, we travel to stone that predates civilization itself. Göbekli Tepe's megalithic precision. You're standing on a barren hilltop in southeastern Turkey. The year is 9600 BCE. Around you, massive T-shaped pillars tower overhead, some reaching 16 feet high. They're covered in intricate carvings: foxes, lions, scorpions, vultures, all rendered with artistic sophistication. The stonework is deliberate, precise, almost architectural. Except this temple wasn't built by Egyptians, or Greeks, or Romans. It was built 6,000 years before the first pyramid by people who supposedly lived in caves and hadn't invented pottery yet. German archaeologist Klaus Schmidt began excavations in 1995 after noticing the hill was artificial, a tell formed by millennia of human construction. What he uncovered redefined prehistory. Radiocarbon dating places construction at 9600 to 8200 BCE, making it 11,600 years old. That's 6,000 years older than Stonehenge, 7,000 years before the pyramids at Giza. The site covers 22 acres. Ground-penetrating radar has identified at least 20 circular enclosures, most still buried. The largest pillars weigh 10 to 20 tons each, carved in situ using stone tools, then transported from quarries over 300 meters away. They feature elaborate bas reliefs of animals, abstract symbols, and what might be the earliest pictographic writing ever discovered. Built by pre-pottery Neolithic people who had no evidence of agriculture, no metallurgy, no permanent settlements. Yet they quarried, carved, moved, and erected these monuments with a precision that suggests advanced spatial reasoning. A 2017 study by Gil Hackley, published in Cambridge Archaeological Journal, revealed that the enclosures follow precise geometric patterns. These weren't random placements. Someone planned the entire complex using geometric principles we assume didn't exist yet. Stone tools found on site show no sign of domestic use. No hearths, no cooking debris, no trash pits. Purely ceremonial, purely monumental. Then, around 8000 BCE, they buried it. Deliberately. Thousands of tons of debris were hauled in to backfill the enclosures, preserving them beneath the earth. This wasn't abandonment. It was ritualistic closure, as if the site had served its purpose and needed to be hidden. The mainstream explanation is straightforward. It represents a pre-pottery Neolithic revolution where organized religion preceded agriculture. Mobile hunter-gatherer groups cooperated seasonally to build ritual centers, motivated by spiritual belief rather than subsistence needs. The complexity proves cognitive sophistication existed long before farming. It's not impossible, just unexpected. But the logistics don't add up. Moving 20-ton stones without wheels, domesticated animals, or metal tools requires hundreds of people working in coordination. That requires feeding them. Construction spanning centuries requires social organization on a scale that supposedly didn't exist yet. Where did these people live? How were they sustained during building seasons? And why would nomadic hunters need to track celestial cycles with such precision? Certain pillars mark solstices and equinoxes, suggesting advanced observational astronomy. Could settled civilization be thousands of years older than we think? Some researchers point to the astronomical alignments and ask uncomfortable questions. If Göbekli Tepe is a beginning, what came before it? If it's an ending, what was lost? The deliberate burial suggests they were hiding something, preserving knowledge in stone for a future that might understand. Or maybe we're the future they were addressing, and we still don't get the message. From stones that challenge the timeline of civilization, we turn to metal that defies modern metallurgy. Damascus steel's lost formula. Hold a Damascus blade to the light and watch patterns flow across the steel like water frozen mid-ripple. Distinctive watery bands called Wootz patterns mark steel so sharp it could slice a falling silk scarf, so strong it could cut through European swords like butter. For over 2,000 years, smiths created this legendary metal. Then, sometime around 1750 CE, the knowledge vanished. Gone, as if it had never existed. Damascus steel appears in historical records as early as 300 BCE in India. Islamic smiths in Damascus perfected techniques between 900 and 1700 CE. The last known swords were forged in the early 1800s. Since then, despite centuries of metallurgical research, electron microscopes, and material science, no one has perfectly recreated it. Original Damascus steel contained 1 to 2% carbon with distinctive banding from carbide structures. In 2006, a study by Reibold and colleagues published in Nature identified something impossible: carbon nanotubes and nanowires in authentic samples. Structures modern science only learned to create in the 1990s. Features that require electron microscopes to even see, embedded in steel forged by smiths using nothing but charcoal furnaces and hand tools. Rockwell hardness tests show Damascus blades maintained edges far longer than European steel of the same era. Historical accounts describe blades cutting through rifle barrels and splitting hairs. A 1995 analysis by Verhoeven at Iowa State University found that trace elements from specific Indian iron ore, tungsten, and vanadium were critical to the structure. The Wootz steel originated in Hyderabad, India, exported as ingots to Damascus for forging. Crucible steelmaking required precise temperature control, 1400 to 1600 degrees Celsius maintained for days. Islamic smiths guarded techniques through oral tradition. No written formulas survive. Production ceased around 1750 CE, possibly when Indian ore deposits depleted, or when master smiths died without passing on their knowledge. The standard explanation is that Damascus steel was exceptional metallurgy, built on empirical knowledge passed through generations. Ancient smiths didn't understand carbon nanotubes, but through trial and error discovered ore combinations and heating cycles that produced them. They didn't need to understand the chemistry, just replicate the results. The loss occurred when specific ore sources depleted, and oral traditions died with their practitioners. It's advanced craft, not lost science. But modern metallurgists with electron microscopes, controlled furnaces, and unlimited resources still can't perfectly replicate it. We understand the chemistry. We've identified the nanostructures. We can make steel that looks similar. Yet something about the process remains elusive, a variable no one has isolated. Modern recreations approximate the appearance, but lack the authentic microstructure and legendary performance. Could the original smiths have understood more than we credit them with? Islamic scientific treatises of the era describe detailed experiments and systematic observations. What if they possessed metallurgical knowledge, later dismissed as alchemy, and lost when libraries burned? The Abbasid House of Wisdom contained countless technical manuals. Most were destroyed during the Mongol invasion of Baghdad in 1258. What secrets went up in smoke? The Damascus steel mystery isn't just about lost technique. It's about lost understanding. Somewhere in the gap between empirical craft and theoretical knowledge, something disappeared that we're still trying to find. From steel that defied replication, we cross an ocean to stone that defies gravity itself. Puma Punku's machine-cut precision. You're standing at nearly 13,000 feet above sea level. The Andean air is thin. Your lungs burn with each breath. Before you lie massive blocks of andesite and diorite, stone harder than most modern drill bits, carved with perfectly straight edges, precise right angles, and interlocking grooves that look CNC machined. Run your finger along the cuts. No tool marks, no imperfections. Surfaces flat to within fractions of a millimeter. The people who made this had no written language, no iron tools, no wheels. So what did they use? Spanish conquistadors found Puma Punku in ruins in the 1500s. Archaeological excavation began in the 1960s. Modern radiocarbon dating settled on 536 to 600 CE, placing it in the Tiwanaku culture. But the precision of stonework continues to baffle engineers who examine it today. The largest blocks weigh 130 tons, carved from single pieces of andesite, which measures 7.0 on the Mohs hardness scale. That's harder than iron. Blocks feature perfectly flat surfaces, measured to tolerances of 1 to 2 millimeters across spans of several meters. Precision 90-degree corners and complex interlocking joints like modern prefabricated construction. Drill holes perfectly circular and uniform in depth, suggesting rotary tools. H-shaped blocks designed to interlock in 3 dimensions without mortar, like cosmic Lego pieces waiting to be assembled. Sandstone quarries were located 10 kilometers away. Andesite quarries were over 90 kilometers away, across Lake Titicaca. No copper or bronze tools have been found on site capable of cutting andesite. Copper is softer than the stone it supposedly carved. A 1995 structural analysis by Protzin and Niles, published in Scientific American, confirmed the impossibility of achieving this precision with known Tiwanaku tools. The entire site appears to have been disassembled. Blocks scattered as if by catastrophic event, earthquake, or deliberate destruction. Yet no intermediate practice stones have been found. Every block shows master-level precision. No apprentice work. No learning curve. Just perfection, scattered across a plateau at the edge of the sky. The mainstream explanation is patient craftsmanship. Tiwanaku engineers used copper tools with abrasive sand slurry. Sand is harder than andesite, so it cuts through friction. The precision resulted from extreme patience and skill developed over generations. Transport used log rollers and human labor, thousands of workers moving stones incrementally across the Altiplano. At this altitude, with this level of organization, it's the peak of what pre-industrial civilization could achieve. But experimental archaeology has tried to replicate the precision using these methods. It doesn't work. Not at this scale. Not at this altitude. Not with these tolerances. Modern engineers with laser levels struggle to match the flatness. How did ancient workers achieve it by eye? How do you move a 130-ton block across 90 kilometers of mountainous terrain using only human muscle and wooden rollers? Some engineers and archaeologists suggest the Tiwanaku possessed lost techniques. Spanish chronicles reference stone softening chemicals, plants whose sap could temporarily make rock pliable. The accounts were dismissed as native superstition. But what if they weren't? Local legends speak of acoustic levitation methods, using sound to move massive stones. Impossible, says physics. But so is what's lying on the ground at Pumapunku. The site's alignment with astronomical events suggests it served as an advanced observatory, requiring precision beyond mere decoration. Why does the site look deliberately destroyed rather than naturally collapsed? What were they building, and why did someone want it unmade? The stones remain, silent witnesses to a technology we've convinced ourselves never existed. From stone that seems machine-cut, we turn to metal that refuses to decay. The Delhi Iron Pillar's rust-proof mystery. It stands 23 feet tall, weighs over 6 tons, and has endured 1,600 monsoons without a single spot of rust. The Delhi Iron Pillar was forged in the 4th century CE, using techniques modern metallurgists still don't fully understand. Touch it. Millions of pilgrims have over the centuries. The metal feels smooth, almost warm. No corrosion, no oxidation. Just pure iron standing in defiance of chemistry itself. The pillar was erected during the Gupta Empire, likely by Chandragupta II, who ruled from 375 to 415 CE. Sanskrit inscriptions on the shaft credit its creation to King Chandra's metalworkers. It originally stood in Udayagiri before being moved to Delhi in the 11th century by Sultan Iltutmish. Scientific study began in the 1960s, when metallurgists realized this shouldn't exist. The pillar weighs 6,614 kilograms. It stands 7.21 meters tall, composed of 98% pure iron, a purity requiring advanced refining techniques. Contains 1% phosphorus, which modern analysis shows creates a protective misowadite layer, an iron-oxygen phosphorus compound. A 2002 study by R. Balasubramaniam, published in Current Science, identified this protective film as just 50 to 600 micrometers thick, thinner than a human hair, but enough to protect tons of iron for over a millennium and a half. The pillar was forged using forge welding, heating, and hammering together over 100 kilograms of wrought iron pieces at a time. This required maintaining temperature of 1200 degrees Celsius or higher across the entire mass during forging. Difficult without modern furnaces. Metallurgical analysis shows no significant corrosion, even in cross-sections. Despite Delhi's monsoon climate, 80% humidity for months annually, the iron remains pristine. Modern attempts to replicate using ancient techniques have failed to achieve the same corrosion resistance. We can make pure iron. We can add phosphorus. We can forge weld pieces together. But we can't make it last like this pillar lasts. The mainstream explanation focuses on chemistry and climate. Ancient Indian ironworkers empirically discovered that high phosphorus content in certain ores created a protective passive layer when forged in low sulfur, low moisture environments. The pillar's initial forging in dry conditions allowed the protective film to form perfectly. Delhi's climate, while humid, lacks the sulfur pollution of modern cities that would penetrate the layer. It's exceptional metallurgy, but explainable through chemistry we now understand. But the protective film theory doesn't explain the forging itself. Creating a 6-ton wrought iron pillar requires welding together hundreds of smaller pieces, while maintaining even temperature throughout the entire mass. Modern forges struggle with such uniform heating. How did 4th century smiths achieve it using charcoal and bellows? The precision required to prevent cold joints or weak spots is extraordinary. One mistake and the whole thing fails. Yet they succeeded on a scale not attempted again for over 1,000 years. Some metallurgists suggest the Gupta smiths possessed systematic knowledge of phosphorus chemistry and heat treatment, knowledge later lost during invasions and cultural disruptions. Ancient Indian texts reference rust-proof iron, suggesting deliberate technique rather than lucky accident. Could they have understood corrosion science at a theoretical level we've assumed was impossible for pre-modern metallurgy? Why haven't similar pillars from the same era been found? If the technique was known, where are the others? Did the knowledge die with a single master smith, or was it deliberately hidden, guarded as a state secret like Greek fire? The pillar stands in Delhi, answering no questions, defying time and rust with equal indifference. From metal that defeats time through purity, we turn to concrete that defeats time through complexity. Roman concrete's self-healing secret. The Pantheon's dome has stood for 1,900 years, still the world's largest unreinforced concrete dome. Roman harbor structures endure beneath Mediterranean waves, while modern concrete crumbles after a few decades of seawater exposure. The recipe was lost for over 1,000 years. When scientists finally analyzed it in the 21st century, they found something impossible. The concrete heals itself. Roman concrete formulas were recorded by engineer Vitruvius in De Architectura, written around 15 BCE. He described mixing ratios and general techniques, but specific methods, curing processes, and secret ingredients were lost after the empire's fall. Modern analysis began in the 1990s, when engineers realized Roman maritime concrete outperformed modern equivalents in durability and longevity. The Pantheon Dome, built in 125 CE, remains the world's largest unreinforced concrete dome at 43 meters diameter. No steel reinforcement, just concrete and geometry. Roman maritime structures at Portus and Caesarea show minimal deterioration after 2,000 plus years underwater. A 2013 study by Jackson and colleagues, published in Proceedings of the National Academy of Sciences, found that Roman concrete uses aluminum tobermorite, a rare mineral that forms through seawater interaction. Modern concrete typically lasts 50 to 100 years before requiring major repairs or replacement. Roman concrete strengthens over centuries through ongoing chemical reactions. The formula combined volcanic ash called pozzolana from specific sources, lime, and seawater. This created crystalline structures that literally grow into cracks, healing damage automatically. A 2017 analysis by Jackson's team in American Mineralogist revealed that seawater triggers growth of aluminum tobermorite crystals in microcracks, sealing them before they can propagate. The concrete contains less lime than modern concrete, reducing carbon emissions by up to 85% compared to modern Portland cement production. Vitruvius described mixing ratios, but exact curing processes and timing weren't fully documented. Modern attempts to recreate it succeed chemically in the laboratory, but fail to match the longevity in real-world applications. Something about the process remains elusive. Roman concrete hardens through pozzolanic reaction, not just hydration like modern concrete. This creates different crystal structures, more stable and reactive to environmental conditions. The standard explanation is empirical discovery. Romans found that volcanic ash from specific sources, especially Campi Flegrae near Naples, created superior hydraulic concrete when mixed with lime and seawater. The formula worked so well because it matched their specific needs. Slow setting, but ultra durable. Perfect for harbor construction and massive public buildings. The knowledge was lost during the Dark Ages when large-scale construction ceased and written records were destroyed by invasions and neglect. But modern concrete science has every advantage. Electron microscopes, chemical analysis, controlled experiments, computer modeling. We can analyze 2,000-year-old Roman concrete down to the molecular level. We know the ingredients. We understand the chemistry. We've identified the self-healing mechanisms. Still, Roman harbor structures outlast modern ones, built with theoretically superior materials, engineered using advanced science. What variable are we missing? Some engineers propose Romans understood concrete chemistry at a deeper level than credited. Recent discoveries of self-healing mechanisms suggest deliberate design, not lucky accident. Could Roman engineers have systematically studied material science, conducting experiments across the empire's vast construction projects? Did they create an empirical database, testing different volcanic ash sources, varying water ratios, documenting results across decades? If so, that database is lost, buried in libraries that burned or books that rotted. Why did medieval Europe abandon such superior technology? When the Roman Empire fell, concrete construction virtually stopped for over 1,000 years. Europe built with stone and brick. The knowledge sat in old books nobody read anymore. By the time concrete made a comeback in the Industrial Age, we had to reinvent it from scratch, and what we reinvented was inferior to what had been forgotten. The Pantheon stands in Rome, its dome defying gravity and time. Tourists photograph it, unaware they're looking at technology we still can't fully replicate. From concrete that defies decay, we travel to stone that defies explanation. The Baalbek Trilithon's impossible mass, 3 limestone blocks. Each weighs approximately 800 tons. They sit 20 feet above ground, fitted so precisely a knife blade can't slip between them. Modern cranes struggle to lift 200 tons. Industrial machinery maxes out around 1,000 tons with extensive preparation and ideal conditions. Yet somehow, 2,000 years ago, possibly much longer, someone moved these stones from a quarry 3/4 of a mile away, lifted them into a temple wall, and fitted them with millimeter precision. No one knows how. The Temple of Jupiter at Baalbek has awed visitors since Roman times. The site was ancient when Romans arrived. They built their temple on top of even older foundations. German expeditions in the early 20th century documented the Trilithon's dimensions in detail. A 4th megalith, the stone of the pregnant woman, still sits in the quarry. It was never moved. It weighs an estimated 1,000 tons or more, the largest worked stone on Earth. Each trilithon stone weighs approximately 800 tons. That's 1.6 million pounds. Stones measure roughly 19 meters long, 4 meters high, 3 meters deep, fitted at a height of 7 meters above ground level. Joints between stones are so tight that metal detectors show no gaps. The precision is frightening. The quarry is located 800 meters from the temple site, not far in normal terms. In megalith terms, it's impossible. The unfinished stone of the pregnant woman in the quarry weighs over 1,000 tons. A fifth megalith discovered in 2014 weighs an estimated 1,650 tons. These would be the largest stones ever moved by humans if they'd been completed and transported. Roman construction techniques documented by Vitruvius describe cranes and pulleys lifting maximum 10 to 20 tons. The largest crane in the Roman world could handle maybe 50 tons under perfect conditions. The modern Liebherr LTM 11,200-9.1 crane, one of the world's largest mobile cranes, maxes out at 1,200 tons under ideal conditions. Moving an 800-ton stone would require extensive preparation, perfect ground conditions, and engineering calculations unavailable in the ancient world. The stones show no evidence of being cut into smaller pieces then reassembled. They're monolithic, solid, unbroken. The mainstream explanation relies on unlimited labor and Roman engineering genius. Engineers at Baalbek were exceptionally skilled, possibly using thousands of workers, wooden rollers, lever systems, and massive ramps to incrementally move the stones. The precision fitting used copper tools and abrasive sand. While extraordinary, it represents the upper limit of Roman engineering capability, applied with unlimited imperial resources and decades of time. Difficult? Yes. Impossible? No. But the math doesn't work. 800 tons across uneven terrain requires overcoming friction forces in the millions of pounds. Wooden rollers would shatter under the weight. Even if they didn't, moving the stone 1 meter would require hundreds of workers. Moving it 800 meters seems impossible. Ramps capable of lifting 800 tons to 7 meters height would need to be massive, requiring more material than the temple itself. And even if you somehow moved them and lifted them, how do you position them with millimeter precision? How do you prevent them from cracking during placement? Some researchers point to evidence the trilithon predates Roman construction by millennia. The megalithic base shows weathering patterns different from Roman masonry built above it. Ancient texts reference Baalbek as the landing place in pre-flood legends. Could the trilithon be remnants of a much older structure the Romans built upon, made by a civilization with lost construction techniques? Local legends speak of giants building the foundation. Mainstream archaeology dismisses this as myth, but myths sometimes preserve memories of things that actually happened. Who built the base of Baalbek? What method could move 800-ton stones across 800 meters? How were they lifted and positioned with such precision? Do the megaliths predate the Roman temple built around them by thousands of years? The stones sit in Lebanon, fitted perfectly, saying nothing. The greatest mystery isn't how they were moved. It's why we're so certain they couldn't have been moved by methods we've forgotten. From stones that seem to mock the laws of physics, we return to craftsmanship that mocks the laws of chemistry. The Lycurgus cup's ancient nanotechnology. Hold the cup to the light and it glows blood red. Light it from within and it turns jade green. The Lycurgus cup has confused scientists since entering the British Museum in the 1950s. It's Roman glass from the 4th century CE. Delicate cagework depicting King Lycurgus tangled in grapevines. It should be simple silica with metal impurities. Standard Roman glasswork. Instead, it contains gold and silver nanoparticles engineered to exact specifications that modern technology only achieved in the 1990s. The Romans created nanotechnology 1,600 years before we invented the electron microscope. The cup entered the British Museum collection in 1958. Early observers noted its unusual optical properties, but assumed it was clever glasswork, nothing more. Light played tricks through colored glass all the time. But in 1990, materials scientist Ian Freestone decided to look closer. What he found shouldn't exist. The glass contains gold and silver nanoparticles, precisely 50 to 100 nanometers in diameter. That's 500 times smaller than a grain of salt. The particles exist in colloidal suspension within the glass matrix. Modern nanoparticle technology wasn't developed until the 1990s. The exact ratio of gold to silver, 7 parts gold to 3 parts silver with trace copper, creates the dichroic effect. Change the ratio and the effect fails. The cup appears jade green in reflected light, ruby red in transmitted light. 2 completely different colors from the same object depending on the light source. A 1990 study by Freestone and colleagues published in Gold Bulletin used electron microscopy to reveal the nanostructure. In 2013, Gang Logan Liu's research at University of Illinois showed the technology could be adapted for extremely sensitive chemical sensors. Modern applications of ancient Roman tech. Only about 50 dichroic glass objects survived from the Roman era. The technique was rare, expensive, guarded. Romans would need to grind gold and silver into particles 1/1000th the width of a human hair. Modern recreations require ultra-precise chemical processes and temperature control measured in degrees. No Roman texts describe the technique. The knowledge was completely lost after the empire's fall. The mainstream explanation is accidental discovery refined through trial and error. Roman glassmakers accidentally discovered the dichroic effect through experimentation with metallic additives. Over generations, they empirically refined the process, probably through adding gold chloride solutions during glassmaking, without understanding the nanoparticle physics involved. Like Damascus steel, expertise came from practice, not theory. They didn't need to understand why it worked, just how to reproduce the results. But achieving such precision accidentally strains credibility. The nanoparticles must be exact size. Too small, and the effect changes. Too large, and it fails completely. Modern chemists with electron microscopes struggle to replicate it consistently, and they can see what they're doing at the nanoscale. How did Romans control particle size to within nanometers using nothing but charcoal furnaces and Bronze Age chemistry? How did they know when to stop the reaction? What visual cues told them the nanoparticles were the right size? Could Roman craftsmen have possessed systematic chemical knowledge far beyond our assumptions? Recent research into ancient alchemy texts shows sophisticated understanding of metallic transformations. Some historians now argue these weren't mystical nonsense, but coded technical manuals, practical chemistry disguised in symbolic language to protect trade secrets. Did Rome have proto-chemistry we've dismissed as superstition? Why were only about 50 dichroic objects made if the technique was known? Was it that difficult? That expensive? Or that secret? Did a single workshop guard the method, dying out without passing on knowledge? The Lycurgus cup sits behind glass in London, glowing red and green, answering no questions. From glass that defies light itself, we climb to stonework that defies earthquakes. Sacsayhuaman's earthquake-proof masonry. You're standing before a wall built from stones weighing up to 200 tons, carved into impossible polygonal shapes with 12 angles, fitted so tightly that 5 centuries of earthquakes that leveled Spanish colonial buildings have left it untouched. Run your hand along the joints. You can't fit a knife blade between them. You can barely see the seams. The Inca had no written language, no iron tools, no wheels, no pulleys. Yet they built earthquake-proof architecture that modern engineers study for seismic design inspiration. Spanish conquistadors found Sacsayhuaman in 1533. Francisco Pizarro's chroniclers described stones joined with such precision that a needle couldn't penetrate the joints. They assumed it was the work of demons, giants, anything but humans. The fortress survived major earthquakes in 1650, 1950, and 1986 that devastated Cusco's Spanish architecture, built right next to it. Spanish buildings collapsed into rubble. Inca walls didn't shift. The largest stone weighs approximately 200 tons. Many exceed 100 tons. Stones feature up to 12 interlocking angles in 3 dimensions. Each stone is unique. No standardization. No identical blocks. Every single piece is custom fit to all adjacent stones. Joints between stones average 1 millimeter or less, tighter than modern concrete construction. The site sits at 12,000 feet altitude. Stones were quarried from locations up to 35 kilometers away, transported across mountainous terrain without wheels or draft animals. No copper or bronze tools have been found capable of carving andesite and diorite, the primary stone types used. These stones measure 7.0 on the Mohs hardness scale. A 2008 study by Protzen, published in Journal of the Society of Architectural Historians, demonstrated that known Inca tools couldn't achieve the precision observed in the stonework. Experimental archaeology has tried repeatedly. Using documented Inca methods, it takes months per stone and achieves nowhere near the precision. The polygonal masonry style requires each stone to be custom fit to all adjacent stones in 3 dimensions. You can't prefabricate. You can't standardize. Every single stone is a unique 3-dimensional puzzle piece. Modern engineers at University of California, Berkeley study the interlocking design for seismic-resistant architecture. The stones can shift slightly during earthquakes without separating. The irregular shapes create mechanical locks that prevent dislodging. It's brilliant engineering that works better than many modern techniques. The mainstream explanation is patient craftsmanship. Inca stonemasons used bronze chisels, stone hammers, and patience measured in decades. They fit stones through endless trial and error. Lift stone, test fit, mark adjustments, lower stone, grind with abrasive sand, repeat. Thousands of times per stone. The polygonal design naturally resists earthquakes because stones can shift without separating. While labor-intensive, it required skill and time, not lost technology. But experimental attempts to replicate the process reveal fundamental problems. How do you lift a 200-ton stone repeatedly to test fit? Modern cranes struggle with this weight. How do you grind adjustments into the top surface of a stone sitting on the ground? How do you cut inward sloping joints that lock in 3 dimensions? The geometry alone is staggering. Each stone must fit perfectly with multiple neighbors while accounting for slopes, curves, and irregular surfaces. Some researchers propose Inca legends of stone-softening plant extracts weren't myths, but references to actual chemical techniques. Spanish chronicles mention such substances, but dismiss them as native superstition. If plants could temporarily soften limestone or volcanic rock, the shaping process becomes explainable, but no such plant has been identified. Others point to acoustic theories, using sound vibration to either levitate or fracture stone along desired lines. Inca oral traditions reference such methods. Physics says it's impossible at this scale, but so is what's standing at Sacsayhuaman. How were 200-ton stones repeatedly lifted and repositioned for fitting? What technique carved complex 3-dimensional interlocking joints? Why haven't similar polygonal structures been found in contemporary cultures if this was standard technology? The walls stand in Peru, fitted perfectly, unmoved by centuries of seismic violence that destroyed everything built after them. From defensive walls that endure, we turn to an offensive weapon that vanished. Greek fires lost incendiary formula. The Arab fleet advances on Constantinople in 672 CE, confident in superior numbers. The Byzantine capital seems doomed. Then, Byzantine ships launch bronze tubes forward, and the sea catches fire. Liquid flames pour across the water, burning despite waves, clinging to wood and flesh like napalm, unquenchable by seawater. Arab sailors dive overboard to escape. The flames follow them beneath the surface. The fleet breaks in panic. For 800 years, Greek fire, pyrothalassian, sea fire, protects Byzantium's walls. Then the formula disappears. To this day, no one knows exactly what it was. Byzantine Emperor Constantine IV deployed Greek fire in 672 CE during the first Arab siege of Constantinople, according to Theophanes, the Confessor's Chronicle written decades later. The weapon was credited to Callinicos of Heliopolis, a Christian refugee from Syria who brought the secret to Constantinople. It remained a Byzantine state secret until the empire's fall in 1453, first used successfully in naval battle of 672 CE, destroying the Arab fleet besieging Constantinople. Theophanes the Confessor and other Byzantine chroniclers describe it burning on water and being sticky like napalm. Anna Komnene's Alexiad, written in 1148 CE, describes it as prepared from resin, sulfur, pitch, naphtha, and quicklime. But that list doesn't explain its unique properties. The substance was delivered through bronze siphons called siphonophoros, mounted on Byzantine dromons, warships specifically designed to carry the weapon. It could be projected as a liquid stream, like a flamethrower, or used in ceramic grenades thrown by hand. Byzantine emperors treated the formula as the highest state secret. Revealing it was punishable by death. The weapon was used successfully in naval battles for over 800 years, from 672 to 1453 CE. Historical accounts describe flames that intensified when water was applied, suggesting a chemical oxidizer that didn't require atmospheric oxygen. Modern historians suggest a base of petroleum or naphtha, naturally occurring in the Middle East, but exact formulation remains unknown. No written formula survived the fall of Constantinople. The knowledge died with the last Byzantine chemists. The standard explanation is petroleum-based incendiary mixture combining naphtha, quicklime, sulfur, and possibly saltpeter. The burning on water effect came from petroleum's lower density, floating on the surface. Quicklime's exothermic reaction with water would make flames burn hotter, explaining why water intensified the fire. It wasn't supernatural, just advanced chemistry for its era. The formula was lost because it was oral knowledge held by a few specialists who died during Constantinople's fall without transmitting it. But modern recreations can't match historical descriptions. We've made napalm. We understand incendiary chemistry. We can make things that burn on water. Yet Byzantine accounts describe flames that water intensified dramatically, that clung to armor like gel, that could be projected in sustained streams for extended periods. Characteristics difficult to explain with known medieval compounds. What ingredient or process are we missing? Some historians propose Greek fire contained metallic compounds, possibly aluminum or magnesium, derived from alum deposits common in Asia Minor. These would create thermite-like reactions that explain the water intensification effect. Thermite burns hot enough to cut through steel and intensifies with water. But aluminum and magnesium weren't isolated as pure metals until the 19th century. Could Byzantines have extracted them in usable form? Others suggest it incorporated phosphorus compounds, which burn spontaneously on contact with air and react violently with water. White phosphorus was known to alchemists. Could Byzantine chemists have isolated reactive metals, or phosphorus we assume weren't discovered until modern chemistry? How was it projected as sustained stream without modern pumping technology? Byzantine siphons worked somehow, but mechanical details are lost. Why did no one outside Byzantium successfully replicate it, despite capturing examples? Arab forces captured Greek fire grenades and siphons during battles. They examined the residue. They interrogated prisoners. Yet they never successfully reproduced it. The formula for Greek fire died in 1453 when Constantinople fell to Ottoman forces. Whatever secrets it contained went up in flames with the city. We're left with descriptions and legends of liquid fire that couldn't be quenched, a weapon so effective it protected an empire for 8 centuries, then vanished as if it had never existed. 10 technologies, 10 impossibilities. From Greece to Peru, from the 4th century BCE to the 17th century CE. Different cultures, different eras, different purposes. Yet one pattern connects them all. Precision beyond their supposed capabilities. The Antikythera Mechanism. Tracking planets with gears not seen again for 1,400 years. Damascus steel containing nanostructures discovered in 2006. Roman concrete that heals itself through chemistry we're still trying to replicate. Göbekli Tepe, built 6,000 years before pyramids by people who supposedly lacked the organization. Stone moved and fitted with tolerances modern engineers struggle to match using computer-aided design. Glass engineered at the nanoscale without any ability to see what they were creating. Chemical formulas guarded so well they died with their creators, taking secrets we're still trying to rediscover. The standard explanation is convergent ingenuity. Ancient people were smarter and more capable than we assume. Given enough time, patience, and motivation, humans can achieve extraordinary things with primitive tools. The precision wasn't impossible, just improbable. The knowledge wasn't advanced, just hard-won through generations of trial and error. When civilizations collapsed, techniques died with their practitioners. We romanticize lost technology because it's more exciting than the truth. They were skilled. We've forgotten how skilled. This explanation works for some things. Patient craftsmanship explains much of what we see in the ancient world. But it struggles with the pattern. Why do these technologies cluster at civilization boundaries, appearing at the dawn of culture or vanishing at its collapse? Why are there no intermediate steps? The Antikythera Mechanism has no predecessors in the archaeological record. Damascus steel has no gradual development we can trace. Roman concrete was perfected, then lost completely for over 1,000 years. Greek fire appeared fully formed and disappeared without a trace. Why does experimental archaeology consistently fail to replicate methods that supposedly used available tools? Researchers have spent decades trying to move stones like those at Baalbek or Pumapunku using Bronze Age technology. They manage small-scale successes, but nothing approaching the originals. Why does each mystery stand alone, disconnected from what came before and after? If these were natural developments, we'd see evolution, gradual improvement, practice pieces, failures. Instead, we see sudden appearance, perfection, then silence. Maybe the question isn't whether ancient people were smarter than we think. Maybe it's whether we're thinking about knowledge itself all wrong. We imagine progress as a straight line upward from cavemen to smartphones. But what if human understanding moves in cycles? Peaks of achievement, followed by catastrophic loss. Knowledge painstakingly rebuilt only to collapse again. Each civilization inheriting fragments, mistaking them for new discoveries. The Antikythera Mechanism might not be the beginning of Greek astronomy. It might be the end. The last survivor of a tradition that reached extraordinary heights, then collapsed when libraries burned and masters died. Damascus steel might be the final echo of metallurgical knowledge developed over millennia, then lost in a single generation. Roman concrete might be the perfection of techniques refined across centuries, lost when the empire fell and cities emptied. We assume lost technology is romantic nonsense because we assume progress only moves forward. But history doesn't support that assumption. The Bronze Age collapse destroyed civilizations across the Mediterranean. Knowledge accumulated over centuries vanished. Writing systems were forgotten. Trade networks dissolved. It took hundreds of years to recover. If it happened once, it could happen again. It probably has happened multiple times, each cycle leaving fewer traces than the last. Most people walk past museum displays, seeing nothing but old rocks and corroded metal. They read the placard, accept the explanation, and move on. They see the Antikythera Mechanism and think, interesting old gears. They see Damascus steel and think, pretty patterns. They see Roman concrete and think, old buildings last a long time. But you made it here. You're wired differently. You see the pattern. You notice what doesn't fit. You ask why when others accept because